Hello, friends. We shall continue our discussion. We will look at the control of synchronous motor drive. The synchronous motor drive control can be obtained by controlling the supply frequency. We know that there is three-phase AC given to the stator of the synchronous motor. Now, controlling that frequency, we can control the synchronous motor speed. We know that the synchronous speed is given by 120 F by P, of which P is a constructional parameter, hence is constant, whereas the frequency is a parameter it's possible to control. The variable frequency, what we mentioned just now, it can be obtained. How to obtain the variable frequency? One thing that immediately we can think of is, because our supply frequency is constant, na? How to get the variable frequency? Immediately, one thing we can think of is have an alternator explicitly for this control purpose and have the output of the alternator variable as much as the frequency is concerned. Are you able to appreciate that? The output of the alternator can be controlled, the frequency and the voltage. If we have such a source, then it can be obtained, but having a separate alternator for controlling the synchronous motor itself is not a good proposition, because the weight and then size of the alternator becomes a limitation. The cost also becomes too much. It's a little odd proposition, so to say, and that is something similar to the Warlier control that we have already come across. However, there is another possibility. We can have the supply frequency variable by using sorry, power electronic converters. We can use power electronic converters and get the supply frequency which is variable, and this approach will be very compact and then economic also. Once when we give such a supply to the synchronous motor, the speed of the motor can be varied. The variable speed can be realized. Now, with this approach, the supply frequency variable, there are two methods. One is called true synchronous mode, another is called self controlled mode. So, using the variable supply frequency, there are two approaches. What are those? True synchronous mode and self controlled mode. First, we'll take up the synchronous motor control by true synchronous mode. Synchronous motor control by true synchronous mode. What is this true synchronous mode? Here, the supply frequency of AC fed to the stator is controlled by an independent oscillator. We get variable frequency, no doubt, and to generate that frequency, we use an independent oscillator. Okay, and the frequency is changed gradually. The frequency is changed gradually, pulling into step the rotor in easy fashion, which will avoid or minimize the hunting oscillations. The biggest problem in the synchronous motor operation is the hunting. When that synchronization or the magnetic locking happens, na, that time there will be these hunting oscillations, and here in this approach the frequency can be changed gradually starting from the minimum, so that we get the rotor coming into the magnetic locking the synchronization in a smooth fashion. The schematic looks like this. Look at the schematic. Please observe this. What are all there in the schematic? We have the synchronous motors. It can be one or multiple motors. And the synchronous motor, there is, in addition to this, we have inverter, we have rectifier, we have AC supply. Here there is inductance L, a capacitance C. And then we have firing circuit, the flux control, delay circuit, reference frequency F star, actual frequency F, the voltage V star expected, reference voltage, so to say. So what are all in this schematic? Reference frequency F star, delay circuit, flux control, firing circuit. All this part turns out to be the control part. Here AC supply, rectifier, L and C, inverter, and then the synchronous motor. This is the schematic. With this schematic, how the working happens, what way the scheme works. In this case, the frequency F star, what I showed here, is the reference frequency. It is the frequency that we want to have, the reference frequency. Then, using this reference frequency, the required frequency F is obtained with a delay. Okay, and this frequency itself is generated using an independent oscillator. Okay, next, the delay circuit I showed here. Why this delay circuit is provided? This delay circuit is provided to give enough time to the motor to respond to the changes. It should not so happen that we will change immediately and expect the motor to respond immediately. It will not happen that way, because this motor is an electromechanical system, whereas changing the frequency is purely electrical system. We know that electrical system time constant is very less, whereas electromagnetic system time constant is high. Motor requires more time to respond. Hence, there is a need to change the frequency keeping this in mind. That is where the delay comes into picture. Very important aspect. Now, the value of F, what we have here with this reference, is used to generate the firing signal or the gating signal alpha, assuming that this rectifier is made up of, consists of the SCRs. SCRs are the controlled power electronic devices. By changing the alpha firing angle of these devices, rectifier output can be changed. We know that. So for a 3-phase AC supply, this will be 3-phase rectifier. Now, by changing the firing angle, the magnitude of this voltage can be changed. And this is rectifier. AC is here, Obviously on this side we have DC, and this DC is fed to an inverter. Inverter changes this DC into AC. Between rectifier and the inverter, we have this DC. This is called DC link. This is called DC link. In this, we have an inductor L, we have a capacitor C. Inductor L is used to smooth the current, C is used to smooth the voltage and stabilize the voltage. The DC voltage will be more stabilized. Next, the frequency what we have here with a delay, that frequency on one side is used to control the value of alpha. On the other side, that frequency acts as a reference for the inverter to operate. This inverter converts DC into AC. When it converts DC into AC, AC of how much frequency? The question comes up. And how much frequency is dictated by this F. That means the output here AC with V and then F both variable. With V and F both variable. There the change in F we require. For that, this acts as a reference input. I told voltage also variable. Voltage also variable. Are you catching? That voltage I can change by changing the input DC itself. The input DC can be changed by changing the rectifier operation, controlling its alpha, and that alpha is again decided by the value of F. Why we change voltage with a change in frequency? Because we want to maintain V by F constant. We want to maintain V by F constant. Why we want to maintain V by F constant? Because this V by F represents the flux, and that remains constant. And once the flux remains constant, torque remains constant. Whole idea is to maintain the torque at constant value. That's why the F what we have here actually is for the pi control, so that we will have the value of V depending on the flux, the torque value I want, that's called as V star. With the value of alpha gives me a DC voltage and hence the AC voltage with the corresponding voltage to frequency ratio remaining constant, giving me the constant torque. Are you able to appreciate this? So here we have the power path wherein AC to DC, DC to AC with the required voltage and frequency such that V by F ratio is constant. Whenever we change F, V is also changed, maintaining torque constant. With the change in frequency, we get change in the speed. Look at the scheme again. Are you able to appreciate this? Good. So, the whole thing we discussed is this. The frequency, F star is the reference frequency. Using F star, the required variable frequency is generated with suitable delay. This delay is provided to give enough time for the motor to respond. Value of F is used to generate firing angle alpha for rectifier to get particular output DC, so that output voltage of inverter is such as to maintain V by F constant. V by F constant. Value of F is input to the inverter to control the frequency of output AC. Thus, we get variable frequency AC with V by F remaining constant, giving us constant torque. And such a supply is given to synchronous motor controlling its speed. Here, L and C, as I mentioned, help to smooth and hold constant the voltage in DC link. The F star is generated using an independent oscillator. So this type of control of the synchronous motor using an external oscillator, independent oscillator, to control the speed of the synchronous motor. I can set it to different values now. To control the speed of the synchronous motor is called true synchronous mode. I repeat, true synchronous mode. Okay, so we shall stop there. Next class we will continue.